Yeah, my name is Sarah. I come from the region here. I live in the region of Karlsruhe. I work with lasers in my work, and I develop things like this. This is an industrial laser system for marking pieces of metal, pieces of plastic in a line where products go through. In my free time, as she mentioned, I'm in the Fab Lab Karlsruhe, where we developed or built the Laser Sour, which is an open source project. And so I have two laser sites, one at work and one in my free time. And so I did an experiment with the CO2 laser in the Fab Lab. I wanted to know what happens when the beam goes on the skin. And the result, so I went to a butcher and bought a piece of pig skins, 5-6 millimeters thick. And I put it on the laser and switched on the fume extraction and said, okay, don't know where to start. And this I come to later. And I ended up with this. On the top, you see 10% input power at 1,000 millimeters minute writing speed. Second line on the top left is 50% of power, and the third is 100%. When you look closely, you can see that the O's and zeros, the meat, the skin was lasered out and fell down. So then I was scared. I was really scared. It smelled like hell. I was close to vomiting. And I thought, whoa, didn't expect this. And the second, on the left-hand side, the 3 rows, were with 8,000 millimeters minute marking speed. I don't want to have this on my skin or in my eyes. Definitely not. This I can't describe, I can't imagine the pain and the consequences, the medical consequences. So therefore, you are responsible for what you do with lasers. Everyone is personally responsible to wear the safety goggles, to take care that no beam goes out of the compartment. So whenever you hurt yourself, don't take me reliable for it. Oh, Sarah didn't warn me about this and that. So, no, absolutely not. You are responsible. So read the standards, read more, read some other literature. Think about what you're going to do. Seriously, think about what you're going to do. It is so dangerous, or can be dangerous. And yeah, obviously, before you switch on the laser system, please switch on your brain. This is vital. This is really important. So, by the way, this was done with a CO2 laser at 10,600 nanometers. And I don't know the optical output power, but the input power was maximum 100 watt. So I guess 60, 70 watt output power optical. Not nice. I came across some, on preparation to this talk, I came across some nice pictures and some nice stories I want to share. Especially what is very vulnerable is the eyes, obviously. Skin you can repair, you go to the hospital emergency room and you get fixed up. With the eyes, it's more difficult, especially in the visible range of light. The top left image, there was a guy who had a setup at home, a 1 watt laser, a blue laser system, and it was standing on a chair. And he did something. I read the story was very vague, but he wanted to switch it off. So he got off his chair where he was sitting to tinker with the system. And he stumbled upon a cable, and the whole laser setup from the other chair fell over. And somehow he got the beam through his eye. This is 1 year after the accident. And I mean, imagine you have this huge spot where you see nothing. I mean, the brain can adapt. But I mean, such a black spot on one eye, you can't ignore this. You look someone in the face and you see black spot. You look on the traffic lights, you see black spot. So this was a very, very bad mishap. On the right image is less energy with a near-infrared laser. This is a typical YAG laser, 1064 nanometers. That's a wavelength I work with at work. That was a short pulse. And this is something you might recover from. Not that the retina recovers, but that your brain adapts to, take away this, I ignore this spot, I interpolate the image. I did the laser talk in autumn in Darmstadt at the MRMCD. And I haven't had the CO2 laser at that time. I just had my laser from work. So I did the same experiment. I got from a butcher this piece of pig skin, placed in the focus area, and said, okay, 20 watt, full throttle, let's see what happens. And after 1 minute of marking a rectangle on the skin, I saw nothing. Well, I mean, I put my power meter, so 20 watts, so everything was right. Then I took my thermal imaging camera and saw, whoa, this is getting hot. The left, you see on the left image, the range goes to 57 degrees. You don't see anything, but it goes into the tissue and heats up from the inside. This must be very painful. I don't want to do it. Sometimes I'm tempted to go through the beam, but I'm not going to do it, just to see the to have the sensation. On the right-hand side, on the bottom, this big red, this glowing blob was 2-3 minutes after marking this, what you see on the left-hand side. And maybe you can read it, what I've written below. This is Hello Welt, Hello World. You see nothing on the skin, but you can see it in the thermal image. I find this very impressive and shows even with lower energy you can do a lot of damage. And this gives, at that wavelength, this gives a lot of damage inside the tissue. Imagine you have your magnifier glass in summer, and you have the sun in the focus, and you have your skin. This starts burning, and this is only minimum power. You have whatever, how big the magnifier is. I don't know. Give it a shot. It's very easy. It's very easy. You take a pot, pour in some water, put it on the oven, on the cooker, heat it up and hold it in your hand, and then a thermometer, and see when the pain starts to become unbearable. So 60 degrees.
So
something.
the question was at which temperature, I think.
Yeah. Anyway, so this is painful. I don't want to do it. I want to show you, I talked about the danger of the optical radiation. We have two more dangerous sources of danger. One is when you handle a gas laser, like a CO2 tube, or different gas mixtures. You need to have a high voltage. The laser at the lab wants to have 3,000 volts, and we give them 30 milliamps. This is deadly. Simple. This is deadly. You touch it, you die, mostly. The other thing is what happens when you apply a lot of energy, thermal energy, onto whatever material. It evaporates, and sometimes the molecules the bonding of the molecules break, and then you have quite some funny things. I made a video with my laser at work. This is 1064 nanometers on a special cardboard which is painted with a lac to see if the geometry is right, if the pulses are right, and so on. But what you see as well, I switched off the fume extraction system, which you can see at the right-hand side, the hose. The smoke that's coming up. This smells bad. And when you do, let's say, 5 to 10 markings on this cardboard, you feel a bad feeling in your tummy. Now, imagine you have some other materials. You have plastics, which is a mixture of different elements and molecules, and they break up, and suddenly you have some delicious things like cyanide, furans, dioxin, chlorine, formaldehyde. Not for me, so I don't want to smell this. I don't want to have this in my system. As well, when you do metal marking, you need to have a fume extraction. When you mark on stainless steel, for example, so it's not just iron, it's other metals as well, and it's an alloy of different metals. So it splits into the elements like nickel, chromium, mangan, cobalt, niobium, beryllium, lead, and so. And when you take ceramics, you have the same yummy, delicious content. So a fume extraction system is very, very important, very vital. If you do something in the region of material marking when you want to change a material. So if you just have a laser pointer and you chase your cat, so this doesn't apply. This is only if you do something with the material. So there's mentioned a standard, EN 11553. This is, I will come to standards later. This is a first introduction into the standards. A lot of things around lasers are standardized. Wavelength to energy and which class it gives, and so on, how thick protective material has to be, how the glasses have to be made of, which answer quite a lot. I will come to this later. I'm going to talk about laser classes now. Should. No, not yet. Some funny things you shouldn't do. On the top left side, top left image, this was last year in the Hack Center. I want to apologize to the Hackspace, to the Stuttgart hackers, because we projected some images at the wall above them, and I was a bit, whoa, is it okay? Is it okay? Okay. So I'm sorry for that. What you see is a 400 milliwatt blue laser standing on an MTC DVD box on a bistro table, which was standing on the normal table, so it was about this high. And then we had a power supply, and then we had a galvanometer control, and so we could deflect the beam. So if someone pushes it just a bit and everything gets misaligned, and someone walks by or doesn't realize it has a blue laser in his eyes. So remember the first images of the eyes, and gives a nice black spot. The image below I found in a book, playing with lasers. I was in the library and collecting my materials, and I came across this image. I said, no way. The subtitle was, please don't look onto reflecting materials. In a book you could buy officially for the youth to tinker with lasers. I mean, this is one of the most stupid ideas, and I will tell you later why this is one of the most stupid ideas. It has to do with laser classes. And what you see on the other side, on the right-hand side, I want to go to vacations. Excuse me. I wanted to go to vacations and I had quite a lot of work to do, programming FPGAs on my laser system. So this is the internal of my laser system, and this is at home. Because I'm a professional trained laser person, I thought, well, I have my safety goggles. I chased the cat away, closed the window blinds, and I did my programming work. And every now and then I had to switch on the laser and to see if everything goes well. So the laser head, this is a gray box on top. The laser beam goes in, there are two galvanometers with mirrors, and then it goes through a lens onto the material where the magic happens. And this brown thingy is a loudspeaker. And what's round is a fiber reinforced tape. On the right-hand side, you see an oscilloscope. I don't say which brand, but it's crap. No, it makes no fun. And what you see in front is the big box. There happens magic. Electricity in, light out. And the rest is control electronics. So I had to do some work at home. And if you don't know what you're doing, so don't do it, please. If you know exactly what you do, maybe you can do it. Talk to other guys, and maybe you better stay alone in that room, not to harm anyone else. Right, laser classes. Basically, there are less laser classes which are interesting for you. We have the laser classes you can see, but for you, as hackers, I think there are 2-3 laser classes interesting. One is laser class 1. I don't know what the old school audio CD players have as a class, but laser class 1 is you take your laser pointer and stare into it, and when you're bored after half an hour, you switch it off and nothing happens. This laser class 1 is interesting for high-powered lasers as well. I come to it later. Class 2 is what you have, what you see here, the laser you chase your cat. It comes with something that we call the eyelid closing reflex. So the theory is that when you get hit by this class 2 laser beam, your eye will close fast enough to avoid any damage. And that's a weak point of this theory. There was a big examination, a big test that had 1,700 people, and they were sitting on a chair and the face was monitored with a high-speed camera, and there was a laser line, and coming down, and they measured the time between laser hitting the eye, coming onto the retina, so you could see the laser beam, and you look away, you close your eyes, whatever, and only 20% of the people closed their eyes within these 250 milliseconds, which the closing reflex talks about. So 80% are not in time. So there were people even who needed 1 second to realize, oh, laser beam, closing eye, or looking away. And in that time, there can be some damage. So even this crap here, this pointer, is not safe for the eye, even if you can buy it everywhere in a photo shop or at a supermarket, whatsoever. Be careful. Then we have class 3. So there is a difference. The classes 1 and 2, they have the M as well. And one is you can stare into it with a magnifier glass, and everything's safe. And the other one is you can't use any optical instruments to be safe in that class. Class 3 is, it's a bit less dangerous than class 4. It is, they talk about 5 times more energetic than class 2. What's really funny is class 4. Everything up from 500 milliamps to megawatt, gigawatt. So this is a class you shouldn't have open like I did on my desk. But you can make it safe. You can have this gigantic hellfire which you have in a fusion reactor as a class 1 laser. You just encapsulate it, that make sure that no laser beam goes out. Then you have a laser class 1 system. So, the classes as well, this is according to the wavelength. There we have the vision, the visible system, the visible wavelength, and you can see it goes up on the right-hand side, where you can see that you have a higher region which is safe within this laser class. This is a region of the eye-safe region, which is about 1,500, 1,800 nanometers, something, I forgot the number now. We have also different damages on the skin in the eye according to the wavelength. UV, you are in the sun for too long, or you like your tanning studio too much, you get burns on your skin. And when you have a UV lamp, you have your glasses, your goggles. So you have different types of photochemical reactions of the skin, especially with the eyes. The UV, you have damage of the cornea. And the longer the wavelength, then you have in UV, you have the damage of the lens. And then you have a damage of the retina. And the longer the wavelength goes, it goes back to damaging the cornea. So when the cornea is damaged, it's stupid, it's bad, but you might be able to fix it, or a doctor might be able, or you can have a new lens, but this is nothing you want to have seriously. So, standards are very important. You can do at home, you can do whatever you want. Buy your 50 watts, 100 watts CO2 tube at the Chinese web shop, they are cheap. You lock your doors, you do what you want, if no one else is in the room. As soon as other people are involved, you should read the standards, which say, for example, the EN 6825, number 1, part 1, has the safety things about a laser system. You have to have a proper housing. You have to monitor any openings, and when you open something, the beam has to be interrupted, and you need to have, up from laser class 3, you need to have a key switch for access control or magnetic card or whatsoever RFID system. In the lab, we want to set up an RFID system for the dangerous machines. So this would satisfy this standard. I could talk 1 week about these standards. They're very complex. They're very worth to read. You can read them. You can't, as far as I know, you can't copy them at the universities which have a technical department. So you go there, you ask for the standards. You ask in Germany, you ask for DIN, EN, whatsoever. In the British, you ask for BS, EN, whatsoever. And you can read them. And, makes no sense to go through the standards. We can talk about it later in the Hack Center, if you like. If you design a laser system, there are some things you should look at. You should monitor every opening, every door. You should have an emergency system. It is a must-have, seriously. And you need to decide if you want to have an emergency shut-off or emergency stop. There are different ideas behind. You need to have a shutter, which interrupts the beam. You need to have some access control. You need, very important, as we saw before, you need to have a fume extraction system. You don't want to have in your space all the chromium and burned wood smell. I mean, before we had a filter system in the lab, when we cut wood, you could smell it hundreds of meters away, half a kilometer you could smell. Oh, in the lab they're burning wood. You need to do a risk analysis. What happens if something goes wrong? What happens if the laser source doesn't respond on please shut off? And this and that. It's a long process of thinking. It has to be taken seriously. There's literature, you should take it seriously. You should document your project. And unfortunately, there is someone who has to sign for what you do, who's liable for this. Finally, who can operate? I think on hackerspaces, who's allowed to operate the laser. So we will have a few short minutes. You will find me if you want to have if you have some questions, if I can help you with your laser design. I'm here. I'm at the Hack Center at the file overflow. You come in the Hack Center very far at the right furthermost corner. If you have questions, then we can discuss your issues with lasers. No problem. I'm delighted to do so. Otherwise, please wear safety goggles. And if you have any questions, we have how many minutes? We are done? I'm sorry. Hack Center. Thank you very much.